Now here what I'm going to do in yesterday's tutorial and also in the lecture you learned how to do Lagrangian tracking and all. Now till now we have mainly focused on tracer particles. When I say tracer particle, it means that these particles are moving to going to move with the velocity of the fluid. But now what happens if these are not tracers? They become heavy or lighter, right? Suppose there are bubbles in the flow, they're not going to follow flow, right? There will be some drag associated with that. Similarly, if you have heavy particles, they're also not going to follow the flow. There is going to be a drag associated with that, right? So what happens if you have those kind of setup? Also, what happens if these particles are not spherical but they are elliptical? If they become non-spherical, how does that going to affect the dynamics? So these are about the passive nature particle. Now what one can do, one can also think about what happens to the living organisms. If you have living organism in the flow, how those organisms are going to behave. So throughout this lecture, what I will do, I will focus on these problems. So I will briefly just try to give you an overview, and what we'll try to learn from here, that even if the flow that is driving these dynamics is not known, because once you say that your particle is no more tracer, it means you do not have information of the flow. If you have particle dynamic, only the particle trajectories, it means that there is an underlying flow plus some other effect that is giving rise to these dynamics, right? So what we'll try to learn here, that we'll generate these artificial setups, okay, and then these tracks, and then using those tracks, can we predict where are going to be attractors, where are going to be repellers? And once you learn, then you can also try to connect it with the experimental observation. So that's the aim of this overall talk. Okay, so let me give you briefly a few examples. For example, if you have like heavy particles, they can, this is a very typical example. If there is anyone who is doing turbulence and they are going to talk about heavy point particles, this is where they will start. So they will say that if you think about cloud formation, right, and it's basically when the rain is going to happen, you have to understand. So cloud is, can you tell me what is cloud made out of? It is water vapor, and only water vapor, or is it a mixture of droplets and liquid droplet and water vapor? It is a mixture, right? But usually the water droplets are of the order of micron size, right? So, sometimes sub-microns also. So if it is of that size, micron size, but when rain happens, the drop sizes are much bigger, right? Millimeter to sometimes it can be even very close to centimeters, right? So those are like much thicker droplet. And usually if you think about condensation, if there is, if only condensation is driving the, droplet formation, means from vapor, water vapor to liquid water, it is going to take really long time to actually, droplet to form. So what happens, turbulence is the one which is in background, or the background flow which is there. Together it drives the condensation. Okay, so that is one example where if you have there is a density difference, and if there is a background flow, that can lead to so basically what will happen, there will be formation of attractive regions, and that leads to droplet formation. So suppose there are two droplets, they come and then they come closer, then they will coalesce, right? But you have to bring them closer. So there are in these clouds these attracting regions, okay, and that's what drives the faster droplet formation. Similarly, one can think about this planet formation, right? So in the early years, like we are talking about billions of years. So what happened at that time, there were dust particles, right? Now these dust particles, of course, they were heavier than the atmosphere around us, and basically what will happen, again, if there is a flow around it, it will drive these dust particles, and then these dust particles will come closer, and then they can coalesce again. If there are two dust particles, they come closer faster, they can stick. Means you can do these kind of tests and you can see. So this is how one can try to understand planetary formation. And then of course one can also think about collective behavior in turbulent environment, right? If there are marine environment, how fish or microorganism, how do they swim together, and how do they try to find the nutrients? So all these problems one can try to, so these are the kind of examples we are going to focus, and how one can try to use the idea of inertial particle dynamics and flow and try to understand it. And again, we'll try to connect it with the pattern formation or structure formation and how repeller and attractor can help us to understand the dynamics. Okay.
Sir,
Yeah.
talking about the reason of attractor or repellers.
Right.
So what is the cause or reason it is coming?
So once we know, then we can try to investigate. That's exactly what Matteo said, that once you know that there are reasons of repeller and attractor, then you can try. So basically the example that was considered in the earlier talk, it was about embryo. We do not have much information. What are the driving forces? What are the mechanical forces? So the information that we have in terms of tracks, everything has been integrated out. Of course there is a flow. If you look at the structure, the early structure where the elongation happens, you can see that there are these counter rotating vertices. It appears like there are counter rotating vertices, and that leads to these elongation, right? And so there is, of course, there is a flow. Then there are other mechanical forces. The mechanical property that comes into picture, it is not a viscous fluid, it is a viscoelastic fluid. That's what we believe, and actually it has been tested, and we know that there are elastic properties that also come into picture. So you don't worry. To begin with, what are the underlying forces? First, you try to understand whether the reason of attractor or repeller exists. Once you have, then you try to dissect them and try to understand that, okay, if this is one possible reason for this, let's knock it out and see how the dynamics is going to get affected. So you break down everything, and then you try to understand the underlying forces, and then you combine, and you can also put weights to different forces, and that's the aim of all these things, right? What are the forces which are working, and how do we? So that is the question that one tries to address, but one can use this kind of approach to address them. Okay, fine. Okay, so here the idea is very simple. So basically, let me. So for example, in case of raindrops, what happens? So basically, okay, let me see. I think, and one of the next examples I have written. So basically, when you think about dust or droplets, so the same dynamics is going to happen. There will be regions of attractors, and it is going to happen in the strain dominated region. I will show later. I will show some videos where you can see. So what will happen? These vertical regions, they will act as a centrifuge, and they will try to push heavier particle outside. Okay, you might have done it in your senior high school. So if there are heavier particles, and if there is a vortex, the heavier particle will be pushed away. Right? So that's what happens. If the particle density is greater than the fluid density, and if there is a rotation that is happening, that those particles will be pushed away from the vertical regions. And once you will be pushed away from the vertical region, where will you go? You will go in the strain dominated region. Let me draw it to explain you what I mean by this. So consider two regions. So the double gyre flow that we are going to talk about, if there are two vertices which are moving like this, counter rotating vertices, so whatever the material you have inside, they will be pushed towards outside of these vertices, right? So where will they come? They will come closer in this region. So this is the region where the strain is very high. Okay, now in these regions, these particles will go, and then they will start to, so if there are droplets, they will start to coalesce. If there are these dust particles, they will go, and then if there is any degree of moisture and all, they can coalesce again. Okay, so that's what happens, and that's how you describe the planet formation. That's how you describe also the raindrop formation. Okay, similarly, you can take another example of like if you think about this phytoplankton plumes in the ocean, again the similar argument you can use. Okay, so here the idea is that compressibility also comes into this. This is a three-dimensional setup, and you can see how the patches are going to form. So let's skip this and let's go to the equation of motion. So the question is how to model these systems. This is good. Okay, so this I had already shown in the earlier case, that you have to solve, if you really want to simulate it, you have to solve Navier-Stokes equation, and then you have to look at what is going to be the dynamics. If there are tracer particles that we have seen before, that you have also tried to simulate in yesterday's lecture, you simply said that the velocity of the particle or these tracers is going to be exactly the velocity of the flow. You do the interpolation and you know exactly what it is going to be. Now if you have a scenario where, so this is the case when you have tracer particles, but now if you say that if suppose particles are heavy, okay, of course this will not be true. There is going to be an additional contribution. If you say particles are lighter, again you are going to have an additional contribution. If you say that particles have their own activity, that is also going to contribute to it. If you say that particles have some how should I put, they are not spherical, right? So if they're not spherical, again that information is also going to come into picture. So we'll try to look at, so what I will do, I will show you the equations that it will describe, and then I will show you the consequences, how the distribution is going to get affected. Okay, that's all we'll try to do.
But we consider them to be point particles.
We'll go for finite particles also. Okay, so we'll consider all the possible scenarios, but of course we'll not be very rigorous. If you want details, there are proper citations there you can go and read. Okay, but here I will give you flavor that how different shape, different degree of activity, the density difference and activity is going to affect, and also finite size. You'll see the finite size has a very beautiful effect. Okay. Oh, this we have already done. Okay. Now, let me skip this video. So this is just to show you that how the particles move around in turbulent flow, and if you wait for some time, you will see that it may go and it can get trapped in one of these vertical regions. So if you wait for some time, you will see. So by the way, this work it is an old work that was done by again Prasad from TFR Hyderabad. Okay, let's wait. Yeah, so you see it goes into one of the vertical structure. This is, by the way, tracer particle. Okay, it goes and it gets trapped, and once it gets trapped in the vertical region, it is going to stay there for some time, and the only way it can exit the vertical region only when the vertex gets destroyed. Okay, that is the only way it can get. Okay, this way. Okay, now you have already done tracer particles. Now what happens if you have a heavy particle? So simplest way to model is, you will say that heavy particle, so of course a flow will try to advect the heavy particle along with it. So it will have a contribution from flow, but then because of its weight, there will be an inertia. It will not be able to follow the flow precisely. So what it will do, the simplest way to model it, it will try to follow the flow with some lag. Okay, that is the simplest possible way. So what you will say, that there is going to be an acceleration term, and in each, so velocity, so if you look at this equation, this is the current velocity of the particle, this is the velocity of the flow at the position of the particle. Okay, so it will not be exactly same. If particle is moving with a velocity and if there is a flow in which it is moving, it will not be exactly same. And if it is not, it will not be exactly same. What will particle try to do? It will try to catch up. It will try to reach the velocity of the flow. Okay, and now how much time it is going to take, that will be defined by tau s, and this comes from this equation. Like what is the density of the, so here rho p and rho f represents the density of the particle and density of the flow. A is the particle radius, mu is the viscosity. So if the density difference is used, it means that the time scale is going to be larger. That means there is going to be a longer time scale for this catch up. Okay, that's how it is going to be. If the density difference is weak, then we know that it will be more or less same, and again it is going to be act as a tracer particle. But if density difference is like significant, you will see what I mean by significant. You will see that then there will be a very interesting dynamics where you will have a preferential sampling. Okay, there could be another scenario where your rho p becomes too large, which means that the time scale it takes to catch up with the fluid velocity is going to be large, right? So by the way, everyone can connect it easily, right? Here the negative sign ensures that this velocity will always try to approach the fluid velocity, right? And this is the time scale that sets how much time it is going to take. Now if rho p becomes large, which means that tau s becomes large, it means it is going to take really long time. And you can also think about, if there are really heavy particles in the flow, whatever you do, it is going to take its own sweet time, right? But of course, since it is in a flow, it will move around. Now in that scenario, if the correlation of the flow so of course, whenever there is a flow, there is going to be a correlation time, right? If the correlation time of the flow is going to be less than this time, it means that the particle dynamics will not have any information of the flow. And in that case, you will see that again it becomes, means the information is getting lost there. Okay, we'll see this example also. Now what one can do, one can define a dimensionless number for these quantities. So tau s is nothing but corresponding time scale, particle time scale, and tau eta is the flow time scale. And based on this ratio, you can say that, so this, using this number, you can actually say that what is the sweet regime where you would like to be to understand the dynamics that we are going to focus on. Okay. Now here what I'm doing, I'm changing the this Stokes time. Okay, this is again a background 2D flow, and in this case the Stokes time is very small, which means your Stokes number is small. In these regimes, your Stokes time is exactly same as the flow time scale, and then you can see the particles are now start to getting accumulated in the regions where the value is 0. So in the background I have plotted vorticity. So you can see that these particles are getting repelled from the vertical region, exactly the same thing I was saying here in this plot. If there are these two counter rotating vertices, the particles will get out of it and then they will try to get accumulated in these regions. So you can see that when your Stokes time is small, which means that the density difference is weak, you don't feel the effect of flow. But as soon as your Stokes time becomes comparable to the flow time scale, you will see that there is a strong correlation, and the particles start to get ejected from these vertical regions, and then they start to get accumulated in these regions. Now again, when your particle time scale becomes even greater than the fluid time scale, at that time the correlation, the information of the flow will not play an important role. So it will try to catch up, but by the time it reaches those the regions which are strain dominated, the flow has already changed its structure. Okay, so what you will see that they will become independent of the flow topology. What is the flow topology at current time, and what is the structure of these particles that is going to be independent of it. Okay, so this is how. So again, you can see. So this is actually a very complex problem, because you can see that these structures are very short-lived. These are not going to be long-lived because there is a strong dynamics. So background flow is moving around constantly. In the earlier example where we focused about the embryo growth, right? So there you can see the dynamics was, so everything was happening over a time scale of 12 hours, 720 minutes. But here things are happening of the order of minutes, right? Minutes or maybe tens of minutes, right? So things are pretty fast. But again, what you can do, if there is a structure, it is short-lived, you can look for those time scales, and then you can try to find that, whether there are regions of attractors or not. And then you can try to do the similar analysis that has already been done. Now, what I will take, so this one is a more controlled example. So here, this is a turbulent flow. So you have seen that in turbulent flow, vertical regions are moving around. But if you have a flow where you have slightly perturbed vertical field, so here I'm plotting a parameter which is known as Okubo-Wise parameter, which is the difference between omega squared minus sigma squared, where omega squared is vorticity, sigma is strain rate tensor. So basically, it tells you that what are the regions of high vorticity and high strain. Okay. So here you can see that all these guys are again going to be in the regions of 0 value, where the vorticity is small. Okay. So here you can see that to begin with, everything was homogeneous, all the particles were homogeneous, but again they go and they get attracted in the regions where the strain is high. Okay. So this is what, but
So what is the
no, actually this is vorticity field. I thought it was Okubo-Wise parameter. It is vorticity field in the background. Yeah.
I'm saying that is that magnitude is also changing, or that those are fixed on?
No. So this is a time. So basically, in the background you have a viscoelastic flow. Okay. So you have a forcing that gives you these counter rotating and rotating vortices like double gyre flow. Okay. But then if you bring in elasticity, you can see that your structure will not be stable anymore. There will be a dynamics associated with it. Okay. So this is what you are going to get. So again, you can see that there are these you can see that these patches are appearing, right? So what I'm trying to say that even from very simple ideas, you can have different kind of patches, and one can try to address the question. One can try to use these techniques to address these questions. Okay. And again, the important thing to note is that even though the underlying flow is Navier-Stokes equation, incompressible flow, but you can see that the phase space is contracting, right? If it was a tracer particle, what would you have expected? If it was a point particle, tracer particle, what do you think would have happened? It will follow the flow, yes. And what will happen to the phase space? If it is a tracer particle, so sorry, go ahead. It will get trapped
want to see some kind of.
In the vertical region, so there will be more particles in the vertical region.
No, the flow is incompressible.
Yes.
So then, I mean, they can't cluster if they just follow the velocity scale.
Exactly, right. So
It will be uniformly distributed.
it will be uniformly distributed, right? Okay, so is the question clear? The question that I'm asking here, I'm using heavy particles. There is a time scale associated with these particles. They will not be able to follow the flow exactly. They will follow the flow with a drag, with a delayed time scale, right? But what if we set that drag to 0? Okay, that means that the acceleration is so high, that means that your particle velocity is exactly same as the fluid velocity, right? Now in that case, what will happen to this? Will you still have some degree of clustering, any preferential? So here you can see that there is a preferential clustering. Preferential because they want to stay in the regions which is low in vorticity, right? So what will happen if you have tracer particles? So basically tracer particles will not have any such preference. And as Rida said that, since we are talking about incompressible flow, so phase space will not contract. Phase space will be as it is. It will be homogeneously distributed. Okay, fine. So again, by the way, I have used point particles here. All the particles are point. They do not have a finite size. And again, going back to the assumption, like, if you think about dust and all, and if they are dilute, one can do this kind of approximation. Yes, Mattia, you.
So how does that the equation for these particles? How do they differ from the? I mean, why didn't you use, for instance, the Maxi-Riley?
No, so it comes from Maxi-Riley.
Okay.
It comes from, but then you remove you say history term is gone, the finite size effect term is gone. So you fraction correction, all those corrections you do because you are in the limit where it is point particle mathematically, and then you say that the only difference is in the density. So this is the term that is going to contribute. Okay. Then okay. Fine. Oh.
No, it goes crazy. I think it's the pointer.
Oh my goodness.
Let's try.
Okay, now one can do all sort of analysis. You can see that since it is going to a phase space is contracting, one can look at the dimensionality, means what is going to be dimension. One can do fractal dimension and all, means all those things are there. We will not be focusing on that. Now let's see what happens if you have light particles. Light particles means the density of these particles are going to be less than the flow, and then you will have an additional contribution. Again, it comes from Maxi-Riley equation. I'm not going to describe how we are going to get it. So how your equation is going to get modified? Again, the particle will not have exact velocity of the flow. It will always try to catch up, but then there will be an additional contribution where you will have beta into A, where A is the acceleration at the fluid acceleration at the point part at the position of the particle. Okay, and together these will give two different time scales, and one can say that what is the density. Means based on density difference, you can actually calculate this parameter beta and this parameter tau p. So these are the control parameters that we have. Now if you have light particles, again using the same idea of centrifuge, what you will observe that all the particles get clustered in the vertical region. And this work was very nice work was done by Cencini in early 2000 I think 2005 2006, where or maybe 2008, where he showed that you can have three setup. When you have like tracer particles, all the particles are going to be homogeneously distributed. If you have heavy particles, all the particles are going to be clustered in the strain dominated region. And this is the case. So of course background flow has not been shown, but it has been quantified in a statistical sense. And in the case where the particles are light, they are going to be clustered in the vertical region. Okay, so you can see that these are attractors which are short-lived, and the life of these attractors are going to be the lifetime of these vertical and strain dominated region. Okay. Now let's jump to the living organisms. So there was this famous experiment done by the group of phi is the swimming number. By swimming number, what we mean that what is the activity of these agents. So basically, if there is a swimmer, it will have its inherent velocity, right? And of course, if it is going to move in a flow is going to have a characteristic velocity. The ratio of these two, how fast you are swimming compared to how fast flow is moving, is going to give you the swimming number. So there are two control parameters in this setup. Okay. Now here in the experiment, so of course in experiment it is much more challenging to control like swimming number, right? Means we know that if it is a motile organism, it will have motility. In the other extreme case, that you kill them, so they will not be motile, right? So that's what you do. So that's what actually they did. Okay, they had motile particles, means motile swimmers, and then they had dead swimmers. Okay, and then you put them in this this kind of flow, double jet flow. Okay, and what they realized that when particles have motility, they have this strong clustering. So this is the density map. Okay, you can see that they start to get clustered in these regions or these regions. Okay, and this is from experiment and this is from simulation. Okay. Okay, so this is the observation. So you can see that activity plays an important role. So if you treat them as a tracer particle, you will see that they will be homogeneously distributed. But as soon as you bring in motility, you can see how nicely the distribution is going to be. Okay? Yeah.
What about the density of this particle here? The density of this
More or less same. But there is no density mismatch. Okay? Yeah. Any other question from the setup? So you can see that there are certain particles which are in the vertical region. The reason why they stay in the vertical region, so if you initialize anything, it takes time to get ejected from the vertical region, right? And the time scale it takes to get ejected from the vertical region is going to be controlled by what is your swimming number. If you can swim faster than the velocity scales of these vorticity, then you can exit it faster. Otherwise, what you will do, slowly you will try to go against the stream, and then you will cross the streamline step by step. So you have like, you're somewhere here, flow will try to rotate you, and if you're swimming, you'll try to go like this. Slowly you will move. If you can swim faster, you can exit this region, and as soon as you exit, you immediately get trapped in these hyperbolic regions. Okay, these are hyperbolic regions. Okay, strain dominated regions.
What is the stability number?
So stability number. Yeah. So psi is point. So they have used different stability number.
What's the so swimming number is the speed of the.
Oh, okay. So stability number. The definition. Yeah. Okay. So the definition is. I need to check. I think. So B is a tumbling. How fast you are going to tumble. So basically, these are gyrotactic particles. So basically, they will try to climb up in z direction, but after some time, they tumble. Okay, so there is a tumbling frequency for that. Yeah. And then the other one, I think it comes from the vorticity, the RMS value of vorticity of the flow. So that's the stability number. So there are two time scale, one that comes from the flow and the other one that comes from the inherent nature of the these particles, and that is going to give you stability number. Okay, so this is the exact setup. This is a homogeneous isotropic simulation where you consider a 3D box, and then you see how the structure is going to be. When these cells are bacteria or phytoplanktons are non-motile, you will see that they are homogeneously distributed. But as soon as you bring in motility and you control the stability number, you can see that the structures start to form. So they are again coherent structures, or high density regions start to form. Okay, fine. So this is this is what the setup is. Okay, and of course this is the equation of motion. Here P is representing the orientation vector, and this is very much similar to what you will see like a Jeffrey equation, where K is representing the preferred direction in which the swimmers are trying to go. Okay, now let's see what happens when you have. So by the way, in the simulation that we have seen before, again point particles have been considered. Okay, those are not finite size particles. Now what happens if you have active Brownian point particles and if they are moving in an imposed flow? Okay, so you will have an equation where your velocity of the particle is nothing but background flow, and then V0 into whatever the preferred direction, in which direction these agents are trying to move. Okay, and then you will have, if you are a non-spherical particle, right, what will happen? You will have a dynamic. So this is Jeffrey equation, your famous Jeffrey equation, where omega is vorticity, alpha is the aspect ratio, means how far you are from your alpha Alpha is a parameter that comes from gamma, and it tells you that how far you are from isotropic state. So if gamma is large, you can see that alpha is going to be large. If gamma is 1, alpha is 0, which means that you are spherical, you are isotropic in nature. So of course, when gamma is 1, which means alpha is 0, this term disappears. For spherical particle, there is not going to be any contribution from this. But as soon as alpha becomes finite, you are going to have a contribution which is going to be something like this, where n is again orientation vector in which these particles are going to move, so in this case it is going to be the natural direction. So these particles are like deformed particles, so they are no more sphere, they are going to be something like this, okay, and this vector is your n vector, okay. Now E is strain rate here, and together with that you are going to have a dynamics. Now if you have a homogeneous, so if you take these kind of particles and if you put them in a a roll mill flow, okay, so you have like these are like negative, these are counter rotating vertices, positive and negative vorticity value at the core. What you will see that if you don't have any non-sphericity, if these are only active, they are going to just behave like this, means they are going to be homogeneously distributed, okay, if they are non-interacting. But non-interacting, which means they do not have any size, and also and they do not have any size. Let me quickly go through this. Okay, so in the earlier examples, what I had shown you the distribution, how the particles are going to be, okay. Now if you say that there is also non-sphericity that comes into picture, now this becomes interesting. Here what I'm showing you the results when alpha is 1. Alpha is 1 correspond to a high non-spherical value, and V is nothing but the ratio of the swimming velocity compared to the flow velocity, okay. Now if you are in a non-spherical particle, which means alpha is equal to 1 correspond to actually rod condition, right, means you are completely elongated thing. If you are rod like particle and if you have a swimming number which is of the order of this, you will see that you will go and you get clustered in this strain dominated region, right. Again, all these calculations have been done for the point particle, they do not have any finite size. And as soon as you start to increase the, so here you can see that V is 0.016. If you increase your value of or activity of these agents, if you approach a value 0.095, what you see that it is no more this sharp, right. You can see that here it's very sharp, means very fine clustered region. But as soon as you increase your velocity, swimming number, let's say, you see that it starts to become wider and wider. So can you tell me why that should be the case? Or can you tell me why there should be a clustering? Any idea, any intuition for this? So now the setup is you have active Brownian particles. So in vertical region they are always rotating, right? So there is so and the strain dominated regions, since there are just vorticity is weak, right? So they will just be moving in this straight line. Okay, so that's how it is going to be. Now, but the question is what you expect. So if you set velocity equal to 0, so in the earlier, if you say that my velocity is 0, right? Then what do you think, what do you expect is going to happen? You say that activity is 0 and you have non-spherical particles. Then what do you think, what is going to be the distribution?
Non-spherical or spherical?
Non-spherical.
Trying to align with the flow.
Yes.
Major axis.
No, that is fine, but I'm talking about the distribution, the density distribution.
Uniform.
Uniform, yes. It doesn't matter. It will be aligned, but it will be homogeneous.
Homogeneous, right? It will always be homogeneous. So it doesn't matter how it is aligned, but here what we are focusing on the density distribution, right? So you'll see that your density distribution is again going to be uniform. But as soon as if any small value of activity you introduce, so it is like a singular value, like any positive velocity will kick in and it will move them to these regions. Okay, but the interesting thing is that if you start increasing your velocity, this activity value, okay, then you will see that these regions will not be sharp, and the reason being because of this activity that it can go out of those regions or those stable regions. Okay. Okay, fine. Again, you can play with this aspect ratio and these velocity values, and then you will.
The second question, should there be a dot at the time?
There is a dot. Sorry. So this is ni dot is there. So okay. Okay. This is standard Jeffrey equation. I think there should be so there is this is ri dot and this is ni dot. This is the dynamics of how the orientation vector is going to be.
Last term is active Brownian.
Yeah, this is ABP, active Brownian particle, and the second term is Jeffrey equation. So that comes into picture only when you have non-sphericity in nature.
Omega is given.
So omega is the flow, background flow. So it is moving in this imposed flow.
Omega
Vorticity. Omega is vorticity. E is the strain rate. Okay, strain rate tensor.
and it doesn't have this TR rotational.
No, means in this case, in this setup, because once you bring in rotational diffusion, that adds up another complexity. But what one can do, so if you recall your standard active Brownian particles, what you will have an additional diffusion, translational diffusion term, right? But what we are doing to make life simpler, we are saying that let's kill the translational noise and then do the analysis here. But of course, you can bring in your translational noise and you can see how things are going to be. Okay.
You said that the asymmetric particles,
Yes.
for if they're round, if there is no activity, they're homogeneous.
Right.
Why?
So basically what you have to do del dot u equal to, you have to set what is going to be the value of del, means divergence of velocity field. So if you set this things, so the thing is that we are setting activity to 0, right? So this term disappears. So they become tracer immediately.
Oh, okay, so there is no inertia.
No, so we are so they are non-spherical, but activity is 0, right? That's the question, right?
Okay.
So once you remove activity, so particle velocity has two contributions. One contribution that comes from the flow. So whenever I write u, that represents the flow velocity, and u in the bracket ri means flow velocity at the position of the particle. Ri is the position of the particle, and v0 ni hat represents the velocity due to the active nature of the particle. So v0 is your self-propulsion speed, and ni is the direction in which you would like to move, and that ni comes from means the non-spherical, means in whether you are like this or what is this vector n hat. Okay, so as soon as you say that my activity goes to 0, this term disappears. Now if you take a divergence of u, this is tracer, means exactly the same argument what you have for tracer, it is going to work for this, and it is going to be homogeneously.
But there is some drag effect.
No, so that we are not taking into account. So of course you can make, so with time will make it more complex. So we'll also bring in inertia. So you will see that what happens if you bring in inertia. Okay. Okay. Any question here from this part? So by the way, this is the example that you have to do in the afternoon. Okay. So what you will do to begin with, you will start from tracer particles. You will put them in this roll mill flow. This flow you have already done, right? Yesterday. You have also evolved tracer, right? Now you will use that information, and then you will try to compute what is going to be FTLE value, and then you will try to see that what are the reasons where eigenvalues are what is the profile of maximum eigenvalue, right? And from there you will try to estimate. Now what you will do, so for tracer particles, all good, everything is fine. But once you bring in this information, then you have to look at the tracks of the particle, and based on the tracks of the particle, you have to estimate what is going to be your eigenvalue. So that is going to be slightly tricky to handle. Okay. So the task will be, you take the flow that you already have, you evolve the particle using this equation. Of course, there will be tutors, they will help you how to do that, and then you have to, calculate what is going to be finite time Lyapunov exponent. So for these guys, these regions are acting as an attractor, right? So that's what you have to identify using FTLE. Okay. Similarly, when you have heavy particles, there also we have seen that these regions are acting as an attractor, right? So today you will try to do two examples. You will have elliptical particles in roll mill flow, and these regions are attractor. You have to use FTLE, and then you have to show that yes, they are actually, even FTLE is showing that they are attractors, right? Similarly, you have to do it for the heavy particles. Okay, so these two examples you have to do today.
How should I understand this aspect ratio and their point?
Aspect ratio and then
When they are point.
There. Okay. So you're saying that if it is a point particle, what is the meaning of aspect ratio? So in reality, there is nothing like point particle. But what we are saying that there will not be. So we are always talking about limiting case. Okay. So. The way in the context we are saying that they are point particle, we are saying that they will not be able to, so they are so small that they will not be able to interact with. So again, we are always considering a dilute suspension. Okay, and then we are saying that they are so small and so dilute suspension that they will never be able to see each other. Okay, and then they are not going to affect the flow that is happening around them. They are so small. So in that spirit, they are point particles. So basically, there will not be any interaction among them, and then they are not going to affect flow. Then in that spirit, you can always consider they are going to be point particle. Okay. So whenever I say point particle, that's what we mean. Okay, so the simplest reason why you want to deal with point particle, because it is a lot easier. First of all, it will not affect the flow. Incorporating the fact that the point particles are finite, they themselves will start to modify your flow, right? So that becomes another complex problem. And then if particles can see each other, then they will have their own interaction, and that will also come in the equation of Ri dot. And we'll see in few minutes how it is going to affect. Okay.
Maybe a comment on this is that the elongation you can think of. Say, think about a very small spindle that you put in the water. This guy, if it's circular, it's very small, as I'm saying. If it's circular, it's just going to be transported, and it's just going to rotate by the vorticity. That's when alpha is equal to 0. But when you start having a little ellipsoid, this guy is also going to feel the shear of the flow.
Right.
So it's going to rotate, not like the vorticity, but the vorticity plus the strain.
Plus the strain, yeah.
That kind of term there. That's, I think, the...
Yeah, that's...
Yeah, okay.
So non-sphericity comes only in the rotational, means how the n vector is going to get modified. That's how it comes. Okay. Fine. Okay. So now what happens if you have finite size? Okay. So if you have active Brownian particle, and once you bring in finite size, so this is without flow. If you don't have any flow, you have active Brownian particles. What you are going to have? You are going to have an equation where you have means. Forget about this URI, that is going to be 0 because we are in the limit where your background flow is 0. You will have V0 multiplied by orientation vector, and then you will have, since there is a finite size, there will be particle-particle interaction. So particles can see each other, and then there is going to be Fij. Okay, that is going to be Fij, and then there is this eta I term. Okay, that is the means translational noise that I was talking about. Then there is a dynamics for the orientation vector, and that is going to be nothing but cos theta I sin theta I. Okay, and this theta I dot is nothing but there is a noise term. Okay, I'm pretty sure majority of you might have seen it earlier, and this is the equation which people use to understand motility-induced phase separation. So basically, if you solve this set of equations, and if you are in the limit where your packing fraction or the number density is large, which is greater than 0.4, 0.5, and if your rotational diffusion or let's say persistence time is large, then what you will see that these guys will start to form clusters. Okay, this interaction Fij is purely repulsive in nature. So basically the way it works, when two particles come in contact, they will see each other, they will repel each other, and that's how it is. So there is no attractive term here in force. Okay, these are hard sphere. Okay, so these are hard sphere, but still you can see that they start to form clusters. That is counterintuitive, right? It means why will you form a cluster? Only if you have attractive to them. So that's why, since they phase separate, and even though they are purely repulsive, that's why people call it motility induced phase separation MIPS regime. This is exactly what in the earlier lecture one student was asking. So if you have motility induced phase separation, you are going to have these kind of regimes. Can FTLE predict it? Can it predict earlier? So first of all, where you are going to form these phase separate states, we don't know. Right, in space, so this happens spontaneously. In space, you cannot predict it. But can you means if you have these data, can you predict earlier that where it is going to form? Okay, so
I have one question in that regard. So, is it possible for dry system? No, right?
Dry system
I
to
mean, if you don't have any background flow or anything. So in that case, will you be able to predict anything with this FTD or?
Yes, exactly. That's the thing. It does not matter if you're moving. There should be some force that is driving it, and if you're going to form a cluster, so in some phase space you are being attracted, right? Maybe Mathiya can. So
yeah, I mean, it really depends on these terms that you have there. I mean, so eta I assume is small.
yeah, translation wise is small. Yeah.
So then you still have a drift, which is V0 and I plus mu Fij.
Right.
So in other words, you solve this system, you're gonna get the position of R, and then that's basically your dynamical system now.
Okay.
And then you can see if there is gonna be some attractions and repellers. I suspect there is. If there is, if you start seeing these objects that do this, I mean. You know, maybe you should guys compute it in the afternoon, because I mean, once you have the code,
they'll go crazy all this.
changing the velocity is very simple, right? So
Yeah, it can be done, and the codes are available, easily available. It is not very challenging. So one can. So this is also one can do, and I'm not sure. I'm actually quite confident that it has not been explored from this point of view. Okay, so whatever examples I have shown till now, it has not been explored from FTLE point of view. Okay, so one can try to use these ideas and try to implement and check it for the first time, that whether it is making sense or not, and whether you can actually predict these things or not. So we can see, you can definitely see that things are being attracted, but whether FTLE is also predicting the same thing or not, and what more can be learned from it. Okay.
So this is but without a background.
Yeah, this is without a background flow.
This is without a background.
MIPS, yes, it is without a background flow.
That is very counterintuitive.
Sorry.
That is very counterintuitive.
So that was the question. That's what Anupriya was asking. That's what Mathiya is saying, that if you have a dynamics, it is a dynamical system. Like when you did the calculation, when you said x dot equal to minus y and y dot equal to x minus. Or I'm changing the minus y. Sorry.
what is the dynamical?
Yeah, what was the
No, right? But still
you can compute, right, where are going to be attacked. So exactly the same way. So here you can say that these are particles, they're moving with this force. Then you can say that let's get rid of it. Let's say there is a flow field and that is driving. These are nothing but tracer, but there is so what you have to find, an effective flow field that is driving. What is so phase flow, exactly the flow map, right, that you have to find. Okay, flow map does not say that there should be actual fluid flow. Okay, so that is very important, that you need to understand. That's the reason I'm giving these weird examples to you, so that you can connect. Okay, fine. So we can do it. If there is flow or no flow, it doesn't matter. Okay, it is it. Sorry.
Yeah, I mean, background flow is one. Any flow, it has to have some flow on its own.
Yeah, means if there is a dynamics, you can say that it is moving with some flow, some route.
What I was confused about was FTLE, I understand we can calculate, but if there is no background flow, then why would these particles cluster at all?
Oh, you're talking about this example,
Yeah.
or any example. So yeah, so we don't know what. So for this we understand very well what happens here. Okay.
So the only forces are repulsion between the particles,
Right.
and active
They have activity.
and just then they form clusters.
Right, but you have to have certain. So there is a threshold value for the activity. Also means actually the ratio. So there will be two time scales that one can get, but the packing fraction also plays an important role. So if you are very dilute, you will not be able to see these clusters. Okay, so that's why if you're dilute,
you're basically asking what is MIPS.
Yeah.
okay, that we can discuss. But that's what MIPS is. Okay. But then what one can do, one can take these active Brownian particles and put them in a background flow, again Rolle flow. Okay, and what you will see, that based on what is the swimming number, so it is exactly V0 is the activity of these guys, and V eta is a characteristic flow. So here it is Kolmogorov like velocity. What you will see, that if the swimming number is very small, then you will have a mixed state. Okay, so what happens? if your velocity is weak, right? So basically flow will drive your dynamics, right? And of course the flow will try to mix things. So you can see that there is some degree of clustering in these vertical regions. But
The V eta
V eta is a Kolmogorov length scale. So basically, for this system you don't worry, but what one can do if you are dealing with a three-dimensional Navier-Stokes equation, there is a energy dissipation rate that is involved, and you consider that it is constant. So using energy dissipation rate and viscosity, so energy dissipation rate gives you a length scale and time scale, and viscosity also gives you a length scale and time scale, which have different dimensionality, and then using that you can extract a velocity, a time scale, and a length scale. So Kolmogorov length scale is nothing but the length scale where your Reynolds number goes to 1. That's the idea.
Okay. So how do I interpret it if I look at the flow, like this vortices? What is it?
No, okay.
Turnover or what is it?
So here, okay. So this V eta is nothing but the velocity of the particle. So here V eta is the largest velocity scale in the system. So basically you define U0 sine x sine y kind of thing, right? For this kind of flow. So let's say this is U0 of the system. So what is so V eta is nothing but a characteristic velocity scale. Since V eta is a characteristic scale everyone uses for the turbulent flow, that's why, just to be consistent with that, we have used the notation. But it is nothing but the characteristic velocity of the background flow. Now if swimming number is small, which means that the particles are moving with swimming with a very small speed, then what will happen? You will have a relatively mixed state. As soon as you start to, I think these are movies. Okay, so what you will see that again, when your swimming number becomes comparable to the flow velocity, you will start to see that these guys again, they start to cluster in these regimes, and if it is too large, it doesn't care about the flow, they will just show MIPS. So this is MIPS. This is the case where you will have a phase separation due to the background flow, and this is the case where you will have mixed state. So again, you can see that this is it. So MIPS we have discussed, right? Then if you have background flow and where you have competing velocity, you can see that there are going to be patterns. Okay, and this comes purely because of the fact that you have a finite size. If you remove the finite size, this disappears immediately. Okay.
This is exactly the thing, like it is avoiding the
vertical regions, right? But the origin is very different. So that's why I'm saying that it does not matter what is the origin. You look at the tracks. First, you try to understand that whether there are attractors or not. You can also see the time scales. So even though the flow can be different, but what kind of particles you have, the time it takes to reach those regions are going. So you can see the difference will be in the time scales and other such things. Okay. Okay. Fine. Now, so we had discussed Vichek model. I had also shown what I had given few examples. So basically what happens here, if you're moving around, you will see your neighbor, and then you will try to align yourself with your neighbors, and then you will just flock, right? We have discussed it in detail. Now what happens if you are in a background flow, okay, or if you are in a marine environment or turbulent flow? So again, you will see that there are going to be interesting. So the question that one can ask is there going to be a flocking even if you are in a turbulent regime? Okay, and what we'll try to do, we'll try to consider a very complex setup so that we can make it as general as possible, and then we'll try to understand whether flocking can happen or not. And again, the question is, flocking can be seen as a pattern that is emerging, right? And can one use the methods that we have learned to predict anything like that? Okay, fine. So I will skip all these things. And of course, it is not like for the first time it has been explored. There has been many work where what you do, you consider a fixed flow. Like in one case, we had considered like roll mill, which we have used quite commonly. But one can use any kind of flow, any background flow. You consider a steady state, steady flow, means there is no dynamics, and you try to see what happens if you have particles which are like Vichek kind of particle. Okay, one can do it in 2D, one can also do it in 3D. So let me jump directly to the equation of motion once, just to give you an idea what is the meaning of it. Now what one can consider that these particles, there could be a density difference. So one possibility is that they are tracer, other possibility is that there could be a density mismatch between the swimmer and the flow itself. The other possibility is that they can be active in nature, right? So if you are active in nature, you are going to have an additional contribution that is going to be V0 eta item. And now how this what is going to be the information about orientation? That comes from the fact that if you are a non-spherical particle, this is how your direction. Okay, these two you have already seen in one of the examples that you will be doing today also. Okay, on top of that, the additional information we are saying that these particles can be inertial, there could be density mismatch, and then we are saying that since we want to model a fish school or microorganism, we are also going to add the information that they can see each other and then they can try to reorient themselves. Okay, and that means that there is going to be Wittek alignment thing. Okay, now if you use all this information, how your flocking is going to get affected. So what we find is that so on the x-axis the Stokes number is being plotted. Stokes number is nothing but time scale of the particle, the lag time divided by the flow time scale. If lag time is large, it means that means if it is comparable to the flow, it means you are in the regime where you will be pushed in the strain dominated region. Remember, for the heavy particles, right? If the time scale, lag time scale is of the order of the flow time scale, it means you will be pushed in these strain dominated region, right? You will be pushed away from the vertical region. So, and then on the y-axis we are plotting the alpha value, which takes into account how non-spherical you are. If alpha is equal to 1, it means that you are rod-like particle. So the range is going from some small value to 1, or both of them are on log scale. So what you will notice that if your radius of interaction is small, let's say 0.03. By the way, all these simulations have been done on a 2 pi cube box. So these numbers will give you an idea. So if it is of the order of 0.03 and there is no swimming, means they don't have any, they are passive particles. So if they are a passive particle, what do you think what is going to happen to, so if the particles are passive, do you think Wittek interaction will act or no? So by here I'm setting v equal to 0, swimming velocity is 0. So they are not passive in that spirit. Okay. So do you think Wittek interaction will have any effect if you set v equal to 0 for this setup?
Can you go to the equation 1 second?
Yeah, sure. So the equations you have, so equations are a little complicated. I will just go through them again. You take into account heavy particle information. You say that particles are heavy. So these are intermediate velocity steps. Okay. So you will say that there is going to be a contribution, that is there is going to be an acceleration. Using that acceleration, you compute what is going to be your v star. Okay. Once you have v star, you say that I'm going to calculate another intermediate step velocity, and that velocity is going to be v star equal to v0 plus n hat. Okay, this is, you take into account activity. Once you have v star hat, you take an averaging. There should be a star is missing here. So you take this v double star hat and then you do averaging of that. Okay, so particle, if you are a particle, you will have one contribution like. So first you will say that there is a density mismatch. I will have a contribution. There will acceleration. You will have a velocity from there. Once I have velocity, on top of that I will add activity. So it will move in a certain direction. Let's say this is how I'm elongated. So I will try to move in this direction. And then on top of that, you will see your neighbors in a radius of interaction Rn. And then you will say that I will try to align myself. So there are 3 different forces working on it. Okay, and I have what I'm trying to do here, since it is complex, so I've broken it down into 3 parts. So you will calculate 2 intermediate velocity, and from that you will get the final velocity that you are interested in. Okay, so first there is information that comes from the heavy inertial particle nature, second that comes due to activity, and third is the alignment. Now the question is, when you set v0 equal to 0, which means swimming number is 0, well, Wittek will be active or no? Wittek,
Is it that by a star or double star?
it is with double star. It is always with double star. Sorry, there is a typo. Sorry. So since you can see, it is always going to be active, right? So it doesn't matter whether the particles themselves can move around or not. You can be advected, right? You can be advected by the flow. That's what is happening here. So you are being advected, and since you are being advected, then you will see your neighbors and then you will try to realign yourself. So you don't have energy to move, translate, but you can reorient yourself. That's the idea. Okay. So you're dead for translation, not for rotation. That's the idea. Okay. So yeah, so that's why you see here that when you are rod-like particle and when your Stokes is high enough, which means that there will be a preferential clustering in the strain dominated region, you can see that there is going to be some degree of flocking. Okay. As soon as you increase your your interaction radius, and also you say that now I'm going to increase my self-propulsion speed, you can see that the flocking region starts to become stronger and stronger. And if you make your velocity even stronger, you say that I'm going to be swim faster than the characteristic flow speed, you will see that flocking appears everywhere. Okay, that means that you can dominate the flow that in which you are moving around. So if that you can do, then Vichek immediately dominates, and this R is a kind of a decent interaction strength, so that you can see your neighbors and you can realign. So that's why you see that in most of the regions there is alignment, except this region. This is a region where your Stokes number is weak, and this is a region where you are not elongated but you are flat. Okay, you are like a disc. Okay, so if that is the scenario, then you will not see flocking. And the reason why that is the case, if Stokes, so now what one needs to understand that how Stokes and non-sphericity or elongation is going to affect your dynamics. So basically, when you are elongated, then it is easier to align. Okay, means there is a flow character, means you are going to align with the largest eigenvalue of the flow of the strain rate tensor. Okay, and the second thing is that Stokes number. Okay, if you are at a Stokes number which is close to 1, which means the lag time and the flow characteristic flow time are comparable, in that limit you will be pushed to the strain dominated region. Okay, which means your local density will go up. Once your local density will go up, then what you will see, you will have more people to align with, and that's how your flocking goes up. Okay, so that's the reason, like in this region, when you're means you are more rod-like, and when you are like intermediate to moderate Stokes number, you can see there is flocking. But as soon as you become flat, and as soon as you become at low Stokes number, you can see that it starts to disappear. Okay, now this is the representation, so you can see that. So basically Stokes number can also be connected with size, because there is an expression that comes as a squared, right? So if you are small and if you are like disk, definitely you are not going to show flocking. If you are large and if you are like disk, then there are some possibility. Again, if you are small and you are rod-like, then also there is possibility. But if you are rod-like and you are large, definitely there is going to be an alignment. Okay, even in the marine environment. So that's the overall picture. That's the gist. Okay.
So basically, like how much they are interacting. Interaction range, if it is increasing, then we will see more.
So here I'm saying that interaction range is same. R interaction is same. Okay. And so here I'm saying that I'm fixing my R interaction. I'm fixing my swimming number. Now how the shape and how the size is going to dominate. Here size can also be directly connected with the Stokes number. Okay.
Some vertical wheel lines also.
Where I think that is a plotting thing. That is a resolution issue. It's not there.
What is this color bar exactly?
Oh, so color bar is order parameter. So order parameter, in which case you can define what is a global order parameter, and that gives you. Okay, it is order parameter. So order parameter represents whether there is flocking or not. Okay. Okay. So I have more content, but I think this is enough for you to be motivated and focus on FTLAs. Okay, and these are still open problems which one can try to address. And you can see the time scales here are very different. In one of the examples which Matthias showed, the time scale was 12 hours. Here the time scales are going to be much shorter. And then we have also looked at the time scales which can be of the order of our own lifetime. Like if you think about Jupiter red spot, the lifetime is like means maybe few hundred years, right? And if you think about the polar vortex, so you can see that there are different time scales, different system size, and things are not straightforward. Okay.
So
Yeah.
can I say, or can I convince myself that suppose now I am not looking any attractor or repeller kind of things, in future I might see that because the time scale is so slow? Can I understand?
It depends on the system. So that's what was drawn here in this plot, right? What does this explain you? This tells you that you may not see the attractors immediately. You might have to wait. And that's exactly what Matteo was saying in the earlier.
What you're saying, yeah.
So
Yeah,
it's
but basically there are, it's actually a very good point because, for instance, in embryos, so embryos develop depending on temperature. So somehow, if you basically lower the temperature, it's like reducing, in some cases, the developmental speed of an embryo. So it's like, you move, I go from here to there, and I go at the normal pace, but then I can go very slow. So if you track me for, I don't know, 5 seconds, in one case I arrive to the door, and in the other case I did only one step. And therefore, this also can cause the emergence or suppression of attractors, repellents, etc. So yeah, it's a very good point, yeah. So it may be that if you observe the system for longer, you're gonna see an attractor, repellent.
But the time scale is not only the reason, right? There could be other, for example,
There could be other things, yeah.
So
yeah,
time scale.
Other thing. Yeah, there could be, yeah.
The time scale only tells you when you are going to observe the structure. That's the question. Like, what are the time scales over which you are going to observe the structure?
I have one more question. Can we intuitively understand for the system what will be the time scale by which we are going to see the attractor or repeller kind of reason?
Yeah, so it's not easy, but it really depends, right? So if you know the equations, let's say linear system, alpha was setting the strength. So 1 over alpha is a time scale. So now if you, let's say alpha is, 1 over alpha is 1 hour. If you integrate for 10 minutes, you're not going to observe anything. If you integrate for 2 hours, you're going to start observing for, things. In general, you don't have that kind of alpha, because to know alpha, you have to know the equation.
Exactly.
Forces. In the general sense, that time is called the Lyapunov of time, which is 1 over the FTLE. So that's going to tell you how long should I wait so that I start seeing appreciable deformation and therefore attractors and repellers. Yeah, so that's maybe the way to start.
It should be less than the coordination time.
That time should be, the Lyapunov of time should be less than the integration time. The Lyapunov of time is going to tell you, if I start a circle, how long does it take to become an ellipsoid of major axis E, the number of, the E, okay? You can pick another threshold, but the Lyapunov of time tells you how much you deform by E. If it takes, 1 hour, and you do the integration time for half an hour, you're not going to observe anything. But if you do more than 1 hour, then you're going to observe these attractors and repellents.
Okay. Very good. Any other question? No, then we'll break for lunch, and then maybe around 2:30 to 2:45, because it's already 1:30. So we'll meet at 2:45. Okay, in the computer.